Okay, so each basic operation in the code counts for 1, as we did all the basic operations like simple assignments, the all are 1. Okay, so we have 4 here, sorry, because I forgot to add this 2, so it would be 4. On here also let me add 2 here, 2 plus, right? Okay, now it's good. Okay, the basic operation executes in the same time no matter what value it is supplied, right? There are some examples. Ignore actual time units. We don't say that this will take such seconds. We do not analyze code on the basis of this the time units. Ignore time for method calls, returns, and declarations. The time that is required for method calling, returning a value to the calling method, or the declaration is not considered, right? The assignment will be considered as we did here, right? When we assigned a 0 to the I and 0 to the j. Okay, so what about constants? Forget the constants. Like C, if there is any constant value C, we will forget that. It becomes less important as n gets larger, and I'll show you that. A constant multiplier like this one, right? This statement is same as this statement 5n, right? So the constant multiplier will become insignificant. Okay, simplifying the formula. When we will simplify the formula, then we will say, by throwing out the constant, we will simply say the cost of that code or this piece of code or this algorithm is n square, right? If we have, this is the cost of some algorithm, and we will say that we simplified it, and we will say it's the cost of this algorithm is n square. Okay, this formula is polynomial. This is a polynomial formula, and we may have terms of various order: constants, linear, quadratic, cubic. We usually discard all but the highest order term, right? We discard all but highest order term, like in this case n square plus 3n plus 5. So we will say n square. The complexity of the code is n square. Now here is the justification. Can we justify big O notation? Big O notation is huge. Big O notation is a huge simplification. Can we justify it? Yes, we can. How? It only makes sense for larger problems, larger problem sizes, right? When we have larger problem size, like if we are going towards 10,000, 20,000 input values or 50,000 input values, in that case, we will see that the highest order term will become dominant. For sufficiently large input sizes, the highest order term swamps all the rest. Let's see here, n square plus 3n plus 5. Now, in this here, the value of n is 0, so everything is 0. So 5 is constant, so it's constant. So the resultant value in the last, the value we will get is 5. If n is 0, the result will be 5, right? If the value is 10, the value of n is 10, then n square is 100, 3n is 30, n is 5. So when we will add all these values, we will get 135, right? Now if n is 100, so n square is 10,000, 3n is 300, and 5 is 5. So the value of the result we are getting is 10,305. As you can see, it's the value of n square is dominating. It has started to dominate. Like if in n square it was 100, and now when the value is 100, the value of n square is 10,000, and the rest of the values is just 305. The addition of the 3n plus 5 is 305. Now let's see this one. The value of n is 1000. N square, it's more than 100,000. It's 1000,000, right? Now the value of 3n is 3000 and the value of 5 is just 5. So the value of these two, 3n plus 5, is 3005. But the value of n square has become dominant, right? The biggest value in this equation is of n square. Now in the case we have n is 10,000, the value of n square is 10 raised to power 8. It's much more higher than the other values. 3n is 3 into 10 raised to power 4 and 5 is just a 5. So as the n is getting larger, the value of n square is dominating on other terms like 3n and 5, right? So in the last case, the value of n we have is 1,100,000. So the value of n square is 10 raised to power 10 and the value of 3n is 3 multiplied by 10 raised to power 5, which is you can say is negligible. So as the value of n is getting larger, the dominant term is the highest order term becomes dominant, and we consider the highest order term in order to find the complexity of the code, right? So if we could reduce this n square to n, then the complexity will decrease, right? And the code will perform better. So here we have a graph in which we have tried to convey that how the complexity increases. So this is the number of input, and this is, you can say, the time. So the equation we have x square plus 3x plus 5. In place of n, I'm using x now. So as you can see, the 5, it's a constant factor, there is no change. 3x, as the value of n is increasing, the value of 3x is increasing a bit. X square, now look at the x square term, right? And here is the complete equation, 3x square plus 3x plus 5. Now here the value of input, the input size is 1 to 10. Now if I increase input size, now you can see the distance from these two bars, the distance of these two bars, the red bar and the green bar, it has reduced, right? Because I have increased input size from 0 to 20, and the n square term is dominating slowly. Now if the input size is becoming larger and larger, then this distance will reduce more, right? So in this way we can say, now here when the input size was 1 to 10, the distance, you can say the distance is more, but when the input size is 20, this distance has been reduced. So in this way we take the highest order term in order to calculate the complexity of the code, and we consider that term only, right? And these are some of the complexities. This is the beta, this is lowest one, and this is the exponential time, this is the highest one. So in this lecture we saw how can we examine the complexity of the code, and in the upcoming lectures we will see more code, we will investigate more code, we will explore more coding examples, and we will see how can we measure their complexity. Thank you for watching.